How would it look if I did a sketch of this parabola? Open up or down?
Down.
Down. Okay, so I know that just in general it's going to look like this. Right? Because A is negative. Okay? So I know if A is negative, it opens down. Now, if I want to find the maximum value of that function, what I'm talking about, when I say maximum value, I'm talking about the y value, right? The value that we're calculating with the function. There is no maximum x value. I could put in as big an x value as I want to. But there is a maximum y value where? Yeah, right there, right? So I want to know right here, if I calculate the coordinates, I want to know what the y coordinate is. Now, what do we call that place on a parabola?
Vertex.
The vertex. So we could do this without a graphing calculator. We know that if we've got a quadratic function in standard form, ax squared plus bx plus c, does anybody remember what the formula is for calculating the x coordinate of the vertex?
Negative b over 2.
Yeah, that's it. Right? X equals negative b over 2a. And then if I want to get the y coordinate, what would I do with that number that I'm creating? Yeah, whatever I get there, it's going to be some number, and I'm just going to plug it in for x into the original function and find the y that goes with it, right? Okay. Now, if you're not, probably not everybody's to the point where they just are completely familiar with what goes in this chapter, but this is a pretty big chapter. Would you agree? It's a lot of stuff. It's really important that between now and the day of the test, you know, this class really progresses. I think by the end of this class, you got to be, I mean, you got to be a pretty good student. You got to be, you know, like a college level student to finish up this. Beginning of the year, it's all review. It's not that big a deal, but we get into some heavier stuff at the end here, and it's good for you guys. Some of you are seniors getting ready to go to college, and this is the best thing I could do for you, more than the math, is just help you get to that point where you can put your skills together to a point where you can succeed. In college, things go a lot faster, and a lot more materials covered, and you got to be organized. Here's what I would do in this situation, what I've done. When I was in college and I had a big test coming up, math or otherwise, what I would always do is I would try to sit down, whatever the topic was we'd covered, I would try to just scratch out a little outline for myself of, not in detail, I just want just a little outline of what we covered. You know, okay, we talked about quadratic functions, so we were able to graphs of quadratics or parabolas. The parabolas, there's 3 different kinds of forms we could graph: vertex form, intercept form, standard form. Just put the information into an outline form. And then, honestly, my original intent when I did that was always, well, I might go back and look at that. How often did I look at it? Almost never. But that wasn't the point. I could have just, in fact, usually after I'd be done, I just would recycle it and be done. The fact that I had gone through the process of having to organize my thinking enough to just jot out a little outline was enough. Just being able to force myself to write it down in a way that made sense to me was all it took to organize that in my brain. I was fine. And so that's, I can't tell you how important that is. If you expect that somehow, just by being in here and seeing it and, you know, and doing some problems, it's not enough. It's really not enough. You got to go that extra step, and you got to maybe, you know, try something like that where you're going to sit down and try to organize the information into some sort of a meaningful whole, so you could say, aha, that's how this stuff fits together. Once you've done that once, you're good, probably forever with it. It'll always be there for you. There's not very much memorization with this stuff, really. I mean, there's a few terms to know, and the few that there are, I think it's worth, you know, addressing. How do you memorize those too? Formulas and terms. This would be more useful probably in a biology class or in a history class or something. But I can remember having some classes. I'm thinking in particular, graduate school, I had this geology class. God, we had to memorize. I mean, it was just tons of stuff. You know, all the rock layers in Oregon and Northern California and all the different, I mean, there's just tons of stuff. And once again, what I would do for that, you know, flashcards work, but the thing I would do the most is I just had a list, and I would sit down and see if I could just organize, like, you know, all of this kind of rock layer. Could I write them all down? This kind of rock layer, could I write them all down? And then I just check and see if I got it. And if I did that a few times, That was all it took. If you just write them down, if you think about them and write them down without trying to look at them, that kind of stuff, it's amazing. If you do that a few times, you're done. You're done and you got it. But you just got to get to a point where you make yourself do that. And it's the part of the class where you're going to need to do that is pretty much here now. Maybe it wasn't in the past, but now you got to start thinking about that stuff a little bit. So this weekend, even, doesn't have to be a lot, but sit down for just a short period of time maybe and start to do that stuff. See if you can just jot down a little outline that summarizes chapter 5. Okay? And this kind of stuff would be included in it. Okay, now back to the topic at hand here. This is what we would do without a graphing calculator. With a graphing calculator, it's dead simple. It'll do it for us. So if I pull up a graphing calculator, come on. If I pull up a graphing calculator, I could go into y equals, maybe.
Technical difficulties.
Yeah. Seriously. Well, wow. That's really not working. Not responding. Of course. Of course. Go away. Come on. All right. Let me pull that up again. Hopefully it'll work.
Don't say. Oh, Jordan. Happy birthday, Michael Jordan.
Is it really?
Yeah.
Serious?
Yep, he's 46, something like that. Or is that
Wow.
That's nice Johnson.
Okay, here we go. So if I go in here into y equals, and I want to put this in there, right? So I'm going to put in negative 12x squared. I don't have to. I don't really need them there. Negative 12x squared minus 2x, same thing as plus negative 2x, minus 3. Okay, now part of the deal is that we got to get used to it, and we're going to work through an issue that involves this today. I got to get this thing where I can see it. I might start off by trying zoom fit, or zoom standard, sorry, zoom 6. And I lucked out this time. I can actually see the parabola, but it's not in a very good spot on the screen. Here's how you want to think about the window. The window is like a rectangular template that you're putting over the XY plane. Okay? There are some things you can do to that. What we want to do is we want to try to take that template and we want to try to fit it to the function that we're looking for. So that template, in this case, I want it to surround him, right? But him only. I don't want to have all this extra space there. So I really want my window to maybe look kind of like that. So if I hit zoom fit, now that's a good question. Watch what happens if I hit zoom fit. And we're going to use it today, and it's a really valuable tool, but you got to be careful with it. If I hit zoom fit, which is zoom 0, it does something kind of nice. It shows us the parabola, but look what it does, and this is maybe okay, actually. That's not a bad idea. If I look at the window, just be careful. Look what it did. Y max is at 10, Y minimum is at negative 1,223. It's going to pull that thing way down into a place where I may not be looking. But in this case, if I'm looking for the vertex, that's probably okay. What I might do here, instead of leaving Y maximum at negative 3, why not push that up a little bit so I can see a little bit of headroom on the top so it's not smashed up against the top of the window? Because if I don't, look what will happen. I've got this thing stuck up here. When I want to try to find that maximum and I want to do something with the calculator, like find a maximum, it's going to, see, it obscures it. It puts that equation up there on the top and it makes it hard to see. So instead, I might just go up to the window and I want to raise where the top of the window is to something like positive I don't know, 200 or something like that. If the bottom is at negative 1200, putting y maximum at positive 200 seems reasonable.
That's why we stand.
And now, whoops, you're right.
Yes.
200. Now if I hit graph, that's a little better. Okay, now I can see the thing pretty well, but that was a good idea. The zoom fit, it's going to take the x minimum and x maximum that I've picked. Here's what it does. It picks the x values I've selected, and it fits the size of the window so the y range is right for me to see the whole function, or a lot of it anyway. Okay? If I want to find the peak of this thing, where do I always go when I want to do stuff with a graph? Where are the tools I use to do stuff to a graph in here? Second calc, yeah, second calc. And then the one I want here is 4, right, for maximum. Now, whenever I do something like this, I get the same prompts back. It wants a left boundary, then a right boundary, and then a guess. So I need to surround the point that I'm looking for and tell the calculator where to look. In this case, it may not seem that important, but next chapter especially, we're going to look at higher degree polynomials that do lots of this kind of thing, where they might have many maxima and many minima. We have to figure out which one we're looking for. So I got to tell it. I'm going to scoot over to the left a little bit and establish that as my left boundary. So I'll hit enter to tell the calculator, there, that's it. That's my left boundary. Now it wants a right boundary with a question mark. So where is that? It wants to know. So I'll scoot over to the right and hit enter. And now I've got my two boundaries, and it wants a guess. So I just go someplace in between and hit enter. And it tells me the x value is at negative 0.0833, blah, 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 but I don't really care. I'm looking for the y value, right? So the y value is negative 2.916 repeated. So to 2 decimal places, which is what I want, negative 2.92. Okay, we got it. That would be the value. Okay, so there's one thing we can do that's helpful with our calculators. Here's another thing. Solve stuff like this. Now, if we have a graphing calculator, we could do this, but it would be hard. If I wanted to solve this thing, think about the work that's involved. I would have to FOIL out x plus 2. So x plus 2 times x plus 2, FOIL it all out, distribute the 2, add 9. On the other side, I would have to FOIL out x plus 10, the quantity x plus 10 times the quantity x plus 10, simplify that, distribute a 10, and add 7. Then I got to push everything to one side, and only then would I have a quadratic equation in standard form that I could either factor, probably not, probably quadratic formula, right? But that's a lot of stuff. Now, can I get to this directly with a graphing calculator? Well, yeah, I can. I can. Here's one way I could do this. I could do this. You can kind of take your pick on this. I'm going to show them both to you, but after this, you probably won't. You can take your pick. We could graph everything on one side of the equation as y1. So we'll call all this stuff right here, for example, y1, and all the stuff on the other side we'll call y2. Okay? So let's do that. Go into y equals, clear that out, and I've got 2 times the quantity x plus 2 squared plus 9. Okay, there's the first one. Go down, second one. I've got 10 times quantity x plus 10 squared plus 7. Okay? Now I got to get this thing graphed where I can see it well. So if I try zoom 6 to start with, there's a pretty good chance I'm not going to see much going on here. Well, I can see a little bit. Looks like I can see just a tiny little dip on that parabola and something over there. So where do I probably want to go if I'm trying to see these things? Where do I want to scoop my template? Kind of up there, right? Okay, so let's try that. What if I went from, say, negative 15 to 0, and then I'll just go zoom fit, how about? See what happens. So window, x min, negative 15, x max, we'll call 0, and then we'll go zoom fit. See what happens here. Okay, there's one of them. There's the other one. Okay, so it looks like they're going to intersect there and maybe again over there, right? Now we want to find the least solution of this. Well, now we've got to talk about what we're looking for, I guess. We're starting to be able to see the parabolas, but what is this solution going to look like? What are we looking for on the graph? If we're looking for when this blue function is equal to the red function, what do you suppose that is? Yeah, intersections, exactly. So we're looking for the intersections of the graphs. Very good. So if we want the least one, that's going to be the first one, or I assume what you mean by that is the one furthest to the left. Right? The least means left. We're going to go that way. So we need to scoot our window a little bit more. We need to go back this way a little bit. So we could go, how about, let's go from negative 25, maybe. Okay, grab, how'd that just small happen there? There we go. Okay, so now we can see it, right? There's one intersection, there's the other. We want the left one, don't we? Right? So to find that, where do we go, do you suppose? Intersection. So second, calc, and then number 5. Okay, now it's going to ask me some stuff. Is that the first curve? Well, yeah, I've only got 2 of them. So there's the first curve. Yes, there's the second curve. But now we can't just hit enter 3 times on this like we did with lines, because we got 2 intersections. So now for my guess, what do I want to do? I want to move this guy from my guess left or right to get near the intersection that I'm trying to find. If I leave it here, it might pick this one, it might pick that one. I want it to pick that one. So I'm going to scoot over to the left until the little guy gets close to that intersection. So how about right there? That's probably close enough. If I hit enter, there it is. Okay, so the x value is at negative 16.5. Now, am I really looking for the y value here? No, there are no y's in that equation. I want to find the x value where these 2 y's are equal to each other, right? So that's my answer. I'm looking for negative 16.5. Okay? That's one way. It's a really handy way to do that. That saved us a lot of time, didn't it? Right? I mean, that would have been pretty ugly to have to go through and do all that algebra. Could have done it, of course, but it would have taken some time. Now, the other way we could do this is we could pull everything over to one side. So let's make it green. We'll add these things. I'm going to subtract all this stuff to the other side. Now, I don't have to be fancy about this. I don't have to simplify it. I've already got this stuff over here. I've already got 2 times the quantity x plus 2 squared plus 9. I just need to subtract both of those terms over to this side. So I'm going to subtract 10 times the quantity x plus 10 squared and subtract 7. Okay? And then what's that all going to be equal to once I put it all on the left? 0. Sure. We're going to have 0 on that side. Okay, so now here's the other option. We could call all of this whole big thing, we could call that y1. Okay, so if we do that, watch what happens. I've already got a lot of that in there, fortunately. That's good. So I'm going to erase this guy, go up here, and just tack this stuff on the end. So I had minus 10 times the quantity x plus 10 squared minus 7. Okay? Now, if I graph this thing, watch what happens. If I hit graph, okay, I can actually see the top of that function right there. I got to move my window down a little bit, though, right? So I'm going to go to window, and it looks like y min is 7, y max is 1,000. I'm going to go from y max is 1,000. How about if I go down to negative 1,000? Did I miss it?
No.
Oops. Yeah.
100,000.
Okay, so there's negative 1,000. That way, at least the x-axis will be in the middle. If I hit graph, those are big numbers, but that's okay. I mean, that's what I see. So now, if I want to find the solution here, what am I looking for? If I'm setting y equal to 0, where does that happen? Not vertex. Not the y-intercept. X-intercept, yeah. Y equals 0 on the x-axis, right? So I want to find the x-intercepts of this function if I pull everything to one side. So I've got two of them. I've got that guy and that guy. Well, which one am I looking for? First one. And I don't even probably need to go through this. If I hit second calc 0, it's going to want a left boundary and a right boundary and all that good stuff. So if I scoot over to the left, I guess I'll do it real quick. If I go over to the left of that x-intercept, that's my left boundary. Go up to the right boundary, go somewhere in between, my guess. What do you know? Negative 16.5, same answer. Okay, so it works. All right, so that's useful. Now, what about, we're going to do some story problems like this.
Right.
Okay, I want to try to make the class as practical as I can, so in the event that you're, if you're shooting a rifle off of a building straight up, you want to probably know what's going on. So if you were to fire a rifle straight up, I'm not endorsing this, but from the top of, no, I'm not. I'm really not. No, I'm not. It's just, well, it's a good ballistics problem. It's kind of interesting. Just listen. Shh, quiet, please. Mitch. If I shoot a bullet straight up off of Taipei 101, that's a really tall tower. I mean, that's tall. I think it's the second highest building in the world. It was the highest for a while, and the one was just built that's taller. 1,670 feet high. That's pretty darn high. Hey, listen, please. Listen. I want you to be able to answer 3 questions for me. There's some stuff that we could directly apply this to. If we want to know, for example, given that the rifle bullets are leaving the rifle at a velocity of 3,000 feet per second, okay, we might want to know how high does the bullet rise. Okay, we could answer that. We might want to know how much time is elapsing before it hits the street below. We might want to know something like, I'm going to change this. This is a bad number. Let's say instead of 1 mile, we're going to make it, let's make it 10 miles. 10 miles, I'll multiply that by 10.
Yeah, what kind of friggin' rifle is this?
Okay, now I want you to tell me, the answers we get are going to surprise you. I want you to tell me if you think this is realistic, and if not, why. But
I'm gonna say yeah.
we could now just listen, please. You have to focus on this. You won't get it. So we need to know what the model is. What's the equation then that predicts the height as a function of time? Now, if we ignore air resistance, this is it. It's very simple. This is the equation we get. Negative 16 t squared plus 3,000 t plus 1670. That's really elementary physics. It's no big deal to come up with that equation. That's going to predict for us, if we imagine that when we shoot the rifle simultaneously, we're starting a very accurate stopwatch. And so the t is just how long the bullet has been in the air since it leaves the rifle, right? Now, what's that graph going to look like? Instead of x, we've got t, but that's a parabola, opening up or down? Down. Okay, so what we've got here is something, there's the y and t axes, and all I'm going to do when I graph this thing is I'm essentially creating a parabola, right? Okay, now what's this doing? What is this parabola measuring? Don't get this picture confused with the trajectory of the bullet. The bullet's going straight up and coming straight down. Yes, sir?
How high is it at certain times?
So there's no.
Say it again. Oh, yeah, that's what it is.
What is at certain times?
That's what this is telling us, exactly. Are you asking me a question?
I thought you were asking.
Oh, I was, and that's good. That's the answer. Yeah. So the answer is this is telling us y is the height of the bullet above street level. Okay? Above street level, t seconds after we shoot the thing. And then eventually it's going to hit the street, right? After a certain amount of time. Now, if I want to find out how high that bullet's gone, where would I look on this graph? Yeah, the vertex, right? If I look at the vertex right here, I'm going to get an x coordinate, which is t, and a y coordinate, which is the height. That's what I'm looking for, right? So do you see a way then that I could use a graphing calculator here? This is just like the problem we did, isn't it? If I pull up the graphing calculator and go back to the, I'll go there. There's my equation. Well, we should be able to go in here and just put that equation in, right? So negative 16. I have to use x's instead of t's on the calculator. X squared plus 3,000 t, or x, plus 1670. Okay, and if I graph that, now if I hit zoom 6, I'm not going to see much. That's what it looks like.
It's just a straight.
Now, the reason it looks pretty straight is because this thing is going to go high. I mean, this parabola is going to be big. And so if I want to see what's going on, I need to make this window a lot bigger, right?
How many zeros?
Okay, well, one thing I could do is I could set the window to, window stands for, and for the x values, those are the t values. What would be the natural starting value for t in this case? 0. That's when we start the stopwatch, right? So we'll put in 0 for x minimum, and now we're just taking a guess. How long do you think the thing's in the air? How many seconds do you think the bullet's in the air? 10 is not going to be enough. 20 is not going to be enough.
Let's put 2 minutes.
Okay, we'll try 100. See if that's good.
Okay.
100 seconds.
Yeah, it's less than 2 minutes.
Okay, if we try 100 seconds, I'm going to use the zoom fit trick, so it'll set the scale for us and see how we did. So zoom 0, and that's not bad. 100 wasn't a bad guess. Probably if we went out there 200, we'd be fine, huh? Okay, so let's go down. Okay, now one other thing I'll point out here, it's kind of useful. This X scale tells me where the tick marks are. Okay, so I might put that on there so in case I misjudge, at least I have a pretty accurate guess of how big I do want the window to be. So why don't I go by tens, how about? So there'll be 20 tick marks. And let's try zoom 0 again. See how we did.
Better, much better.
Oh man, that's perfect. Yeah, we're great. Okay, so there's the peak we're looking for, right? I'm going to go ahead and once again, this is just for aesthetics. I'm going to push the top up a little bit so we have a little extra room. So I'm at 142,000. If I go up to like 170,000
Is that feet?
feet, yeah,
That's almost higher than Everest.
it's a lot higher than Everest. Actually, no, it's not. It'd be almost though. You're right. It wouldn't be quite as high. It'd be close. So maybe this isn't realistic. We'll see. We'll maybe talk about why at the end if there's time. Talk a little physics.
Why?
Where are doppelgangers applying them?
I can tell you why it's not realistic. Wind resistance. Air resistance, whatever.
It's not a very
Oops,
Fail.
I miscalculated a little bit. Did I put? Oh, I put 1.8 million.
One too many
Shoot
zeros.
an apple off someone's head.
There. How's that?
Try.
Okay, so we could find up here, let's go up and find the maximum. So second calc 4. Okay, I need the left boundary. Boom, right value. Okay, there's my right boundary. My guess would just be somewhere in between. And the answer is 142,295. Now, what does this x value mean here? About 90, roughly 94. How many seconds it would take to get to the peak? So that's the maximum height. Now, if I divide that by 5,280, that's pretty big. mean, that's telling me that is something like, oh man. I mean, that's telling me that it's just ridiculous. That's so much higher than Everest. Everest is only almost 30,000 feet.
Like 29.
So that's I mean, could you conceivably shoot a bullet that's going to go higher than Everest from the ground?
I can, from the looks of that,
I mean,
it's going to
maybe, but it's not going to go. It's definitely not going to go more than almost 5 times the height of Everest. I don't think so.
I can't really
Okay.
go into orbit.
So what's going on here?
Maybe an artillery
Just a
shot.
little bit. I'll sneak a little bit of physics into this. What's going on is that when something is going that fast,
Air resistance.
air resistance. Try even this. If you're driving down the road at 5 miles an hour, sometime, put your hand on a calm day. There's no wind. Put your hand out the
That
window.
hurts.
Watch the speedometer.
What do you?
Put your face out the window.
Slow
Watch your
down.
face. What do you notice about your hand going 5 miles an hour?
It goes back.
It gets ripped backwards.
At 5? No, right now, 5.
There's a
At
light.
5.
There's a calm breeze.
At 5, you're not going to notice hardly anything. But if you're going 65 or 70, I mean, it makes a big difference, right? So imagine if something, now 60 miles an hour, that's going to be roughly, let's see, that's going to be about, that's going to be about 190 odd feet per second, okay? Pretty close to that, not quite, a little less than that. Now imagine something going 3,000 feet per second. My goodness, that thing is going to be experiencing wind resistance that is literally like going through a solid. I mean, that bullet is going to be highly impacted by the air, and so its trajectory is nothing close to this. Yeah.
You know they have a metal alloy thing that like they found it, I guess, and it's like air.
Well, it's better if it's slipperier. Then the slipperier the metal,
It has like no.
the better it cuts through the air. But you can't have no air resistance because air is a fluid. Even if you had something that had zero friction, that had zero coefficient of friction, it's still got to go through the air and part the air, and so it's still going to slow it down. It'd be like trying to push something that was coated in grease through the water. It's going to slip through pretty easily, but it's still, if that thing gets dropped off a bridge when it hits the water, it's going to slow down. Right? I mean, it's because it's still got a part of the fluid. So that makes a big difference, but that would be a huge deal. If you really wanted to find something that was where the ballistics were going to be really flat, and then you'd want to have something that were very slippery to the air. Now, what about the other questions, though? There were a couple more questions we were dealing with here. We wanted to know, let's see, we wanted to know how much time elapses before it hits the street below. Okay. Where would that be on our graph?
X-intercept.
Right there. Yeah, I'd want to find that 0, wouldn't I? And we know how to do that. We've done one like that. Now, here's the last one I want to do, and then we're good for the day. During what interval of time is the bullet higher than 10 miles? Okay, now how could I do that? This is really important. This is a great trick. Great trick. You won't probably see in the books. Very good one. How could we know on our graph when this thing is higher than 10 miles? What do you think? Oh, I thought you had a suggestion. Anybody got a suggestion?
Put in x equals greater than 10 miles.
Okay, there's the, if we could somehow put something in there so we could have a line at 10 miles, which is 52,800 feet.
Go to the y equals. But
Aha.
Inequality.
I don't need inequality, actually. If I go to y equals, and for y2, if I put in 52,800, think what that's going to do. That's going to graph a horizontal line. This is really cool. It graphs a horizontal line at 10 miles, right?
And then intercept.
So I can see on here every place where that bullet is above 10 miles. Now, if I wanted to find, what I'm going to ask you on the study guide and the test for something like this is I want to know when does the projectile first reach a height of 10 miles, right? So where would that be on the graph?
At the intersection.
Ah, right there. Where would it leave? Where would it last?
the other one.
Yeah, right here. That's when it would fall through. It'd be higher than 10 miles, and that's where it falls through a height of 10 miles, right? So I could just find that intersection, just second, calc, intersect, and then I'm just going to go down. First curve, yeah. Second curve, yeah. Then I just want to go over here, close to this guy, and make my guess. Okay, that's probably good enough right there. So if I take my guess, it's at 18.96 seconds is how long it would take. Okay. Now, one more little interesting tidbit, and then we'll call it quits. If I had something, let's once again ignore friction. This went pretty high, but it came back down. Can you see that if I were able to launch a projectile fast enough, it would actually leave the Earth's, I mean, we could put it into orbit, right? We could put it into orbit or even leave orbit. We wanted to leave orbit to push this thing out so it just never stopped going and never came down. It'd have to go pretty fast. You know how fast it'd have to go?
Too fast.
It would have to go 13,200 meters per second.
8 miles per hour.
So that would be, you know, that there you're talking about like about 30,000 feet per second. Would do it.
And how many miles per
Never
hour?
come back. Yeah, if you can ignore air resistance.
Can we chill out for about 5 minutes?
Yes, you can.